So let's start exploring the properties of our partial molar quantities. Okay. To do this, I want to define a term known as additivity. Okay. All right, and so additivity is a case where you have an extensive property M, and this extensive property is additive when it follows this relationship, where your extensive property M, which is a function of T, P, and then the total moles in the mixture, so for emphasis I'll just call it N total. That extensive property is additive when it follows this relationship. Ni Mi of the pure component T and P. Okay? So a mixture is additive when the extensive property of the entire mixture is just essentially the sum of the moles of one component times the molar property of that pure component. Okay? All right, so this is what it means to be additive. And so if that's true, then what that means is that our partial molar property for a certain species at some temperature, pressure, and composition is just equal to the molar property of the pure species at some temperature and pressure. Okay? So that's the idea there. And for a quick proof on the applicability of this relationship, we know that the partial molar quantity is just equal to the partial derivative of the total molar property with respect to Ni at a constant T, P, and constant moles of species that aren't the ith species. For M, we could plug in this relationship. So we get dni summation of Ni Mi. Or actually, the indices here should be different because we're looking at more than just the ith species. Okay? And in that case, if we take the derivative of the sum, right, only one of the terms in this sum is the ith species. So if we take the derivative of that sum, the only derivative that's going to be non-zero is for the case where j is equal to I. And so what we get back out is the molar property of j is equal to I. So that means that the partial molar property of the ith species is just going to be equal to the pure molar property for that species. Okay? Right? And so I want to emphasize that this relationship that I derive, the above, is true for ideal solutions. Right? In which the sizes and the interactions of the two different species, or the species in the mixture, are all about the same, or are very similar. But if you're dealing with non-ideal solutions, then that statement is not true. Not true. Okay? All right. Instead, we need to figure out a way to actually identify how we could calculate the total molar property. All right. And so the way we do this, or at least the approach we're going to take in quantifying non-ideality, is going to be by introducing what I call the partial molar change upon mixing. Okay. All right, and so this partial molar, or this molar change upon mixing, I'll write it like this. So it's going to be delta M mix. Sometimes, well, before I do that, so this delta M mix is just going to be equal to the total M property at some T, P, and total minus the ideal solution prediction. Okay, at some temperature and pressure. And so this is how, essentially what we're saying is this is how that molar, that volume, that enthalpy, that entropy, this is how that property would change once we start mixing together the different chemicals. And that our actual value, the difference between the actual value and the one predicted by the ideal solution model, that difference would correspond to your delta M mix. Okay? I'll say at this point that you'll also see this referred to as your excess value. So M excess. And so just to make sure you're not confused, delta M mix and M excess, those are the same exact things. Okay? But your book uses delta M mix, so that's the terminology that I'm going to use. Okay, and so this is the extensive form of delta M mix. But we could also define a partial molar form of delta M mix. So with the bar over it. And that is, once again, just going to be the partial molar derivative of delta M mix at some constant T, P, J not equal to I. And what we would get is that that's just the partial molar quantity for species I minus the pure molar quantity. Okay? All right, and so